Pedal Systems is one of the leading companies in India which is engaged in UAV design and manufacturing. It also focuses on many UAV domains such as UAV training, GIS survey, aerial survey, and design services. Pedal Systems is offering you this course Rocket Science. To know more about us, feel free to visit our website or write us to the following mail ID. The content for today's class is following. So, rocket science, that is, we will cover some basic concepts which are related to rocket science, that is, rocket systems and rocket staging. What are different systems associated with the rocket, and what is rocket staging, why it is required, and different types of rocket staging. Then we will cover about some information of space transportation, that is, what exactly is space transportation and what are the means through which we can achieve it. Lastly, we will discuss about current and future rocket technologies. So, what are current rocket technologies available around the globe, and what are the future aspects of the same? So, we will discuss all of the following. So, let's begin with rocket systems and rocket staging. So, there are major four systems of a rocket, that is structural system, payload system, guidance system, and propulsion system. Firstly, we will discuss about structural system. So, a structural system consists only the components, systems associated with the entire structure. So, the structural system, it only consists the components and the systems which are associated with the entire structure. That is, main is the entire body of the rocket, that is, we call it a structure. Different components associated with this structure, etc., are all included under structural system. So, we need a streamlined shape because this streamlined shape will give us less friction. So when we get less friction, we get more speed. If we get more speed, then we will get less distance we have to cover. Less distance we have to cover, then we will need less fuel. And if there is less fuel, then that means there is low cost. So every time we are optimizing a problem where the cost of the entire program is reduced. So this is how we go step by step for any rocket structural system. So for any rocket, we have to take care of different parameters. So some of the parameters are the thermal stability and structural stability. In thermal stability, the outer skin of rocket gets temperature of around 1649 degrees Celsius. This is very high temperature. So we have to take care that when a rocket is escaping the earth, structural body of a rocket should not get destroyed. That's why thermal layer protection gives slow heat transfer. That is, the heat transfer between the body, that is structure, and the friction which is created due to the atmosphere is reduced. So we provide an insulator, that is silica tubes at outer layer. So this is how the thermal protection layer is given to a structure of rocket. Then it comes to structural stability. That is, high weight is expensive and hard to carry. So we have to keep as low as weight such that we get more performance. And then to make it lightweight, one has to use aluminium or titanium, which have lower molecular weight, but at the same time they are strong, such that they can sustain the structural stability, the shocks which are created, and maintain the cruised flight. So this is all about structural system. So here in the figure we can clearly see different systems of rocket. So the structure system includes all the different parts of a rocket, that is from tip to the bottom. Next we will discuss about payload system. So payload system we see at the top from nose. It consists of the systems and components associated with the payload of the mission. And payload is the load carried throughout the mission. So based on what mission we are going on, the payload is kept inside the system such that this payload is carried to the orbit or to the place where the rocket is going. So the type of load to carry is based on type of mission. So for communication missions, satellites are loaded. In that capsule, satellites will be loaded. For living atmosphere missions, humans are loaded. For research, space probes are loaded. Even cargo is loaded for in-space mission happening like International Space Station. So these are the different missions based on which the payloads are carried in the capsule of the rocket and it is transferred to the orbit or where the rocket has been constructed to go for. So this is all about payload system, basically everything that is associated with the payload. Then the next system is guidance system. So guidance system we see is just next after the payload system. So it controls the rocket and its movement. Different components like guidance computers, sophisticated sensors, radars, communication centers, etc. are used. So we have a rocket engine is running and it is moving in a direction. But at some point, we have to control the movement of the rocket. So, to control this movement, a guidance system is used. So, guidance computers are used such that they guide the rocket's speed and direction. So, the measurement of speed and direction has to be taken and handled carefully. So, guidance computers are provided. Then, sophisticated sensors are used to measure the speed, position, and temperatures. So these sensors are located at some different location for different rockets. So this measures the speed, position and temperatures. Radars are used to protect the rocket from the space debris and flying objects moving towards the rockets. So it is used to keep a track of the rocket. Then communication centers are used to transfer the information from space to Earth ground stations. So if a rocket is going outside the Earth and some data is generated in space, so these communication centers are used to transfer this data from space to the Earth. Then the next system, that is the last system, is propulsion system. So this covers the remaining part of a rocket. So rocket's major portion is the propulsion system. Even from figure it is very clear because it consists various parts of a rocket engine. Fuel and oxidizer tanks, pumps, combustion chamber and nozzle. Fuel and oxidizers are allowed to enter into the combustion chamber, are ignited with help of igniter, and then the exhaust gases are allowed to expand through the nozzle in downward direction, thus producing thrust in upward direction. That is the Newton's third law of motion, that is every action has equal and opposite reaction. That is, more the thrust, more fast the rocket will escape the Earth's atmosphere. So we have to create very high velocities of the exhaust gases to expand through the nozzle. The higher values of thrust also produces around 200 dB of sound waves which bounce back from ground and can destroy the whole rocket while launching. Because of this, at the time of launch, using the water resources on a launch pad, that is, water is spread so that sound waves and heat are captured downward and do not reach the rocket. So if we have seen any rocket launch, then we have noticed that water is spread around when the rocket is launching, such that the sound waves which are created due to the rocket launch are balanced back and they do not reach the rocket. So this completes the propulsion system and the four different types of rocket systems. Next we will discuss about rocket staging. Often rocket launch video we have seen these kind of stages associated with the rocket. So we will discuss what is rocket staging and why it is required. So all rockets use the thrust generated by a propulsion system to overcome the weight of the rocket. For full-scale satellite launchers, the weight of the payload is only a small portion of the liftoff weight. Because we have seen in the payload system, the upper capsule which is located close to the nose is having the payload which is supposed to be placed inside any orbit or out of Earth's atmosphere into space. So the weight of that payload is very less as compared to the portion of the weight of the entire rocket. So most of the weight of the rocket is the weight of the propellants because we have to take the rocket outside of the Earth's atmosphere in seconds, and so we need more amount of thrust to be generated. So if we need more amount of thrust to be generated, we need more propellants to be burned. So that's why most of the weight of the rocket is the weight of these propellants. As the propellants are burned off during the powered ascent, a large portion of the weight of the vehicle becomes the near empty tankage and structure that was required when the vehicle was fully loaded. So once the propellants are burned, there are empty tanks located inside the boosters. So in order to lighten the weight of the vehicle to achieve orbital velocity, most launchers discard a portion of the vehicle in a process called staging. So this is the process of staging where we discard the portion of a vehicle, so a portion called the boosters or the stages which are associated with the rocket. This process is called as rocket staging. And to reduce the weight of the rocket during the powered ascent, the stages are discarded after some time when they are emptied. So discuss different types of rocket staging. So first one is serial rocket staging. So in figure it is very clear that before staging, that is in powered ascent, there is a single body, a single rocket which is in blue color. The red one is the nozzle and grey color is the exhaust plumes which are generated of a rocket. Done with the staging, then we can see that upper stage is fired and the first stage is discarded and it is moving in downward direction towards the earth. So in serial staging, there is a small second stage rocket that is placed on top of a large first-stage rocket. The first stage is ignited at launch and burns throughout the powered ascent until its propellants are exhausted. The first stage engine is then extinguished, the second stage separates from the first stage, and the second stage engine is ignited. The payload is carried atop the second stage into orbit. Serial staging was used on Saturn V rockets. The Saturn V was a three-stage rocket which performed two staging maneuvers on its way to Earth orbit. So the one which is discarded is the first stage, and second stage is always located on the top of the first stage, and second stage consists the payload which is light in weight. So once all the propellants are burnt inside the first stage engine is extinguished and second stage separates from the first stage and the second stage engine is ignited. So this is how serial rocket staging is done. Next we will discuss about parallel rocket staging. So for parallel rocket staging we can see that there is one main rocket body and two other small boosters are attached to the main body during powered ascent, and when the staging is performed these strap-on boosters are discarded and the sustainer continues firing, that is the main rocket continues firing. In parallel staging, several small first stages are strapped onto a central sustainer rocket and at launch all of the engines are ignited. When the propellants and the strap-ons are extinguished, the strap-on rockets are discarded. Thus the sustainer engine continues burning and the payload is carried atop the sustainer rocket into orbit. Parallel staging is used on Space Shuttle. The discarded solid rocket boosters are retrieved from the ocean, refilled with propellant and used again on the shuttle. So in parallel staging, strap-on boosters are used which are small compared to the sustainer. Sustainer is the main rocket body. So once all the propellant is ignited and burnt, the strap-ons are discarded and the sustainer flies into the orbit. Some launchers like the Titan III and Delta II use both parallel and serial staging. The Titan III has a liquid-powered two-stage Titan II for a sustainer and two solid rocket strap-ons at launch. After the solids are discarded, the sustainer engine of the Titan II burns until its fuel is exhausted. Then the second stage of Titan II is burned, carrying the payload to orbit. The Titan III is another example of a three-stage rocket. So these are the applications where this series and parallel rocket staging is used. So what happens to this detached or discarded stages? So once they are discarded from a main rocket, what happens to this rocket stages or the strap-on boosters? The spent upper stages of launch vehicles are a significant source of space debris remaining in orbit, in a non-operation state for many years after use, and occasionally large debris fields created from a breakup of single upper stage while in orbit. So earlier what was done that once the strap-ons or the stages are detached, they were not retrieved and they were allowed to move into the space, thus creating the space debris. Since the 1990s, when an upper stage is spent, astronauts have generally dumped any remaining fuel or discharged batteries, passivating them to reduce risks while those stages continue to orbit. So from 1990s, passivation was done, that is, whatever the garbage they are dumping into the space, they were taking care that it should not produce any harm for any entity inside the space. Prior to that, many Soviet and US space programs often did not passivate the upper stages after mission completion. And that's why more space debris has created because of many space programs which were not properly handled and still the space debris are seen inside the space. During most launches, the first stage runs out of fuel prior to achieving orbit. When the first stage is separated, it continues along its suborbital trajectory and falls back to Earth. The second stage, however, is usually the stage that gets the satellite into orbit, which means the stage itself is in the orbit as well. When the second stage separates, it will continue in its orbit indefinitely unless it encounters atmospheric drag. However, companies like SpaceX often like to reprint their second stages as to not leave junk in orbit. So earlier these stages were moving around Earth into the space because these were left unpassivated, then they were carried towards the ocean, or sometimes when they re-entered the Earth's atmosphere, they were burned. But nowadays, companies like SpaceX is producing reusable stages which can be later used again for a launch mission. So this covers the rocket systems and rocket staging. Next we will enter into space transportation. So to exit the space or the atmosphere of Earth, we need an escape velocity because we cannot just move in upward direction without drag, and we need to escape the Earth's gravity. That's why the name is escape velocity. In celestial mechanics, escape velocity or escape speed is the minimum speed needed for a free, non-propelled object to escape from the gravitational influence of a primary body, thus reaching an infinite distance from it. It is typically stated as an ideal speed, ignoring atmospheric friction. A rocket continuously accelerated by its exhaust can escape without ever reaching escape speed since it continues to add kinetic energy from its engines. It can achieve escape at any speed, given sufficient propellant to provide new acceleration to rocket to counter gravity's deceleration and thus maintain its speed. It can achieve escape at any speed, given sufficient propellant to provide new acceleration to the rocket to counter gravity's deceleration and thus maintain its speed. So this is all about escape velocity, and we will see there are different escape velocities for different planets. So based on what gravitational force they have or what gravity they have, it can be decided that how fast a rocket would have to go to leave for every planet. So we can see for first four planets, that is Mercury, Venus, Earth and Mars, there is little bit difference. But if we see for Jupiter, it is moving very fast, and then for Saturn it is moving little bit fine, and then Uranus and Neptune it is okay. So this is completely based on relation with the gravity. So if we see for Sun, then it will be relative to the Sun's gravity. So for Earth we need 11.186 meter per second escape velocity. So Jupiter we can see it is 60.20, while for Saturn it is 36 meter per second. So this is completely based on the gravity which these planets exhibit. Moving on to the orbits. So we have discussed about escape velocity and rockets. Basically, why these terms are studied? Because we need to do space transportation. What is space transportation is we are moving from one location in space to another location. That is, we are moving from Earth to some another place inside the space. So what is this place? Basically, it is an orbit. So an orbit is the curved path that an object in space, such as the star, planet, moon, asteroid, or spacecraft, takes around another object due to gravity. So these orbits are created because of gravity. Objects of similar mass orbit each other with neither object at the center, while small objects orbit around larger objects. In our solar system, the moon orbits Earth and Earth orbits the sun, but that does not mean the larger object remains completely still. Because of gravity, Earth is pulled slightly from its center by the moon, which is why tides form in our ocean, and our sun is pulled slightly from its center by Earth and other planets. When rockets launch our satellites, they put them into orbit in space. Their gravity keeps the satellite on its required orbit in the same way that gravity keeps the moon in orbit around Earth. So we call moon as the natural satellite, but if we are placing any satellite inside Earth or Earth's orbit, then the gravity will keep the satellite to move in its required orbit. So we'll see what are different types of orbits, that is geostationary orbit, low Earth orbit, medium Earth orbit, polar orbit and sun synchronous orbit, then transfer orbits and geostationary transfer orbit, lastly the Lagrange points. So we'll discuss each of them in detail. So first, geostationary orbit. So satellites in geostationary orbit, that is GEO, circle Earth above the equator from west to east following Earth's rotation, because we know that Earth rotates in a direction from west to east. That is, it takes around 23 hours 56 minutes and 4 seconds by traveling at exactly the same rate as Earth. So that's why if we are looking for a geostationary orbit, if we see from a particular point, we will notice that the satellite which is moving in geostationary orbit, it will exactly be looking at us. That is, we won't see that it is moving because at each point it is moving with the rotational speed of the Earth. This makes satellites in GEO appear to be stationary over a fixed position. In order to perfectly match Earth's rotation, the speed of GEO satellites should be about 3 km per second at an altitude of 35,786 km. This is much farther from Earth's surface compared to many satellites. So this was about geostationary orbits. Next we will see low Earth and medium Earth orbits. So a low Earth orbit, which is called as LEO, is, as the name suggests, an orbit that is relatively close to Earth's surface. It is normally at an altitude of less than 1000 km but could be as low as 160 km above Earth, which is low compared to other orbits, but still very far from Earth's surface. Because generally we know the aircrafts which fly, they fly around maximum 12 kilometers, and the value which is specified here is 160 kilometers. So for a low Earth orbit or medium Earth orbit, the range is around 160 kilometer to 1000 kilometer. Unlike satellites in GEO that must always orbit along Earth's equator, LEO satellites do not always have to follow a particular path around Earth in the same way. Their plane can be tilted, so they are not entirely moving in the same direction as GEO satellites. They can also be tilted. This means there are more available routes for satellites in LEO, which is one of the reasons why LEO is a very commonly used orbit. Medium Earth orbit comprises a wide range of orbits anywhere between LEO and GEO. It is similar to LEO in that it also does not need to take specific paths around Earth, and it is used by a variety of satellites with many different applications. It is very commonly used by navigation satellites like the European Galileo system. So medium Earth orbit comes between LEO and GEO, and it has many different applications in which it can be used. Next orbit we have is polar orbit and sun synchronous orbit. So satellites in polar orbits usually travel past Earth from north to south rather than from east to west, passing roughly over Earth's poles. So earlier we have seen GEOs, they travel past the Earth's equator, while as polar orbits travel from north to south, that is around Earth's poles. Satellites in a polar orbit do not have to pass the north and south pole precisely. Even a deviation with 20 to 30 degrees is still classed as a polar orbit. Polar orbits are a type of low Earth orbit as they are at low altitudes between 200 to 1000 kilometers. So in figure we can see there are two orbits, that is two satellites are orbiting around Earth in two different orbits. So one which is moving vertically, that is the polar orbit, and one which is moving horizontally with a slight tilt is geostationary orbit. The sun synchronous orbit, which is called as SSO, is a particular kind of polar orbit. Satellites in SSO traveling over the polar regions are sun synchronous with the sun. This means they are synchronized to always be in the same fixed position relative to the sun. This means that the satellite always visits the same spot at the same local time. This means that the satellite always visits the same spot at the same local time. That is, for example, passing the city of Paris every day at noon exactly. So that's why they are called as sun synchronous orbit. This means that the satellite will always observe a point on the Earth as if constantly at the same time of the day. It serves a number of applications. For example, it means that scientists and those who use the satellite images can compare how somewhere changes over time. So with the help of this sun synchronous satellites, many applications can be predicted. If any change is happening at a particular location, then it can be tracked and understood with the help of sun synchronous orbits. Next, we will discuss about transfer orbit. So, transfer orbits are a special kind of orbit used to get from one orbit to another. When satellites are launched from Earth and carried to space with launch vehicles such as Ariane 5, the satellites are not always placed directly on their final orbit. Often, the satellites are instead placed on a transfer orbit, an orbit where, by using relatively little energy from built in motors, the satellite or spacecraft can move from one orbit to another. This allows a satellite to reach, for example, a higher altitude orbit like GEO without actually needing the launch vehicle to go all the way to this altitude, which would require more effort. This is like taking a shortcut. Reaching GEO in this way is an example of one of the most common transfer orbits called geostationary transfer orbit, that is GTO. So here in figure we can see a satellite is rotating around the Earth and then it starts to transfer from one orbit to another. So basically this is the transfer orbit. So by means of various techniques we can achieve this transfer of a satellite from one orbit to another orbit. Next, lastly we will discuss about Lagrange points. So Lagrange points or L points allow for orbits that are much farther away, over 1,000,000 kilometers, and do not orbit Earth directly. These are specific points far out in space where the gravitational fields of Earth and Sun combine in such a way that spacecraft that orbit them remain stable and can thus be anchored relative to Earth. So these L points are located very far away from Earth. Thus the gravitational fields of Earth and Sun can combine in such a way that spacecraft that orbit them remain stable and can thus be anchored relative to Earth. If a spacecraft was launched to other points in space very distant from Earth, they would naturally fall into an orbit around the Sun, and those spacecraft would soon end up far from Earth, making communication difficult. Instead, spacecraft launched to these special L points stay fixed and remain close to Earth with minimal effort without going into a different orbit. So based on different missions or different applications, the use of L points can be made. So now we have discussed about some aspects of space transportation, that is escape velocity, what is the speed needed to exit the Earth's atmosphere, and then if we are able to achieve this escape velocity, then we will be placing our satellite or spacecraft into an orbit. Then again we have seen, based on various applications and based on various ranges from Earth's surface, there are different types of orbits. Now we will see how we can achieve this. So with help of space launch vehicle. So a launch vehicle is a rocket propelled vehicle used to carry a payload from Earth's surface to space, usually to Earth orbit or beyond. A launch system includes the launch vehicle, launch pad, vehicle assembly and fueling systems, range safety and other related infrastructure. The launch of a spacecraft comprises a period of powered flight during which the vehicle rises above Earth's atmosphere and accelerates at least to orbital velocity. Powered flight ends when the rocket's last stage burns out and the spacecraft separates and continues in free fall. A sampling of launch vehicles of interest to interplanetary mission follows. One useful measure of performance for comparison among launch vehicles is the amount of mass it can lift off to geosynchronous transfer orbit, that is GTO. So the rocket which we consider is also a space launch vehicle which is used to carry this payload into an orbit, basically exiting the Earth's atmosphere with the escape velocity. And it consists of launch vehicle, launch pad, vehicle assembly and fueling systems, then range safety and other related infrastructures for a launch mission. Once all the engine fuel is burned out, the spacecraft is discarded from the space launch vehicle and it is allowed to move freely in the orbit. So the performance comparison for space launch vehicle is based on how much amount of mass it can lift off into geosynchronous transfer orbit. So here to the right we have an image where we can see different comparisons of space launch vehicles. So based on the height this comparison is done. So the first rocket which was used by Germans was V2 rocket which was constructed, which is very small as compared to other rockets. Then it was R7 which was constructed by USSR. Then US constructed a very big rocket till now, that is Saturn V. Then US also programmed space shuttle. Then ESA, that is European Space Agency, has Arena 5. Then again US have Delta 4 Heavy. Then Russia has Proton. China has C2-2F. So these are different space launch vehicles of different countries. Some space launch vehicles of our India are, in India it started with sounding rockets, then it was SLV which was learning phase, that is we understood how we can launch these vehicles from Earth's orbit, which was around in 1960s to 1970s, and it was used to place the spacecraft into LEO and the payload carrying capacity was 40 kgs. Then it was ASLV, that is experimental phase. Then we were experimenting this SLV to ASLV. This was around in 1980s where the payload capacity was increased from 40 kgs to 150 kgs and the spacecraft was placed into LEO. Then it went into PSLV and GSLV, that is operational phase, that is from 1990s. India started its own space launch vehicle programs with PSLV and GSLV. So this PSLV weighted around 1600 kgs of payload, and for GSLV it was 2000 kgs, and it can be used to transfer spacecraft to geosynchronous transfer orbit. Then we have the Mega Space Launch Vehicle, that is GSLV Mk3, which is still used in our country, that is expansion phase, and it was used after 2000, and the payload carrying capacity of this GSLV Mark III is 4000 kgs, and it can be used in geosynchronous transfer orbits as well. So these are different space launch vehicles of India. Next we will discuss about space launch window. A launch window is the span of time during which a launch may take place while satisfying the constraints imposed by safety and mission objectives. For an interplanetary launch, the window is the constraint typically within a number of weeks by the location of Earth in its orbit around the Sun, in order to permit the vehicle to use Earth's orbital motion for its trajectory, while timing it to arrive at its destination when the target planet is in position. The launch window may also be constrained to a number of hours each day in order to take best advantage of Earth's rotational motion. So, to the right, we can see how we can take advantage of Earth's orbital velocity, Earth's rotational velocity, to place a certain spacecraft into orbit or to go for an interplanetary mission. So this window in which we can take help of Earth's rotational velocity or orbital velocity and make happen the interplanetary missions is called launch window. Then one more thing which is very useful for launching any payload into orbit is launch sites. If a spacecraft is launched from a site near Earth's equator, it can take optimum advantage of the Earth's substantial rotational speed. Sitting on the launch pad near the equator, it is already moving at a speed of around 1650 km per hour relative to Earth's center. This can be applied to the speed required to Earth the orbit, that is approximately 28,000 km per hour. Compared to a launch far from the equator, the equator-launched vehicle would need less propellant, or a given vehicle can launch a more massive spacecraft. A spacecraft intended for a high-inclination Earth orbit has no such free ride though. For interplanetary launches, the vehicle have to take advantage of Earth's orbital motion as well to accommodate the limited energy available from today's launch vehicles. So even the Earth's equator has the advantage for a space launch vehicle. That is, if we are launching a vehicle from near to the Earth's equator, then it will give the advantage of moving at high speed, that is Earth's substantial rotational speed. And thus this benefit has been gifted to our India because our location is placed near to the equator, and thus the launches are carried out from Sriharikota, which is close to Earth's equator. Next we will discuss about Space Shuttle. The Space Shuttle is a retired, particularly reusable, low Earth orbit spacecraft system operated from 1981 to 2011 by the US National Aeronautics and Space Administration, that is NASA, as part of the Space Shuttle program. So we have often seen this, that a plane is placed on the space launch vehicle. So Space Shuttle is a retired spacecraft system by NASA which was part of Space Shuttle program. Its official program name was Space Transportation System, that is STS, taken from a 1969 plan for a system of reusable spacecraft, where it was the only item funded for development. The first STS-1 of the 4 orbital test flights occurred in 1981, leading to operational flights STS-5 beginning in 1982. 5 complete Space Shuttle orbiter vehicles were built and flown on a total of 135 missions from 1981 to 2001, launched from the Kennedy Space Center (KSC) in Florida. Operational missions launched numerous satellites, interplanetary probes, and the Hubble Space Telescope, conducted science experiments in orbit, participated in Shuttle Mir program with Russia, and participated in construction and servicing of International Space Station (ISS). The Space Shuttle fleet's total mission time was 1323 days. So this was a little brief about the Space Shuttle program. For Space Shuttle, the first orbiter Enterprise was built in 1976 and used in approach and landing tests ALT but had no orbital capability. 4 fully operational orbiters were initially built, that is Columbia, Challenger, Discovery, and Atlantis. Of these, 2 were lost in mission accidents, that is Challenger in 1986 and Columbia in 2003, with a total of 14 astronauts killed. So here the GIF of Challenger disaster shows how it was crashed in several seconds. The disaster was caused by the failure of 2 redundant O-ring seals in a joint in the space shuttle's right solid rocket booster. The record low temperature of the launch reduced the elasticity of the rubber O-rings, reducing their ability to seal the joints. The broken seals caused a breach into the joint shortly after liftoff, which allowed pressurized gas from within the solid rocket booster to leak and burn through the wall to the adjacent external fuel tank. This led to the separation of the right-hand solid rocket booster's aft attachment, which caused it to crash into the external tank, which caused a structural failure of the external tank and an explosion. Following the explosion, the orbiter, which included the crew compartment, was broken up by the aerodynamic forces. So this was a great loss for Challenger back in 1980s. While as Columbia was crashed in 2003, so during the STS-107 launch, a piece of the insulative foam broke off from the space shuttle external tank and struck the thermal protection layer tiles on the Earth's left. Similar foam shielding had occurred during previous space shuttle launches, causing damage that ranged from minor to nearly catastrophic. But some engineers suspected that the damage to Columbia was more serious. Before re-entry, NASA managers had limited the investigation, reasoning that the crew could not have fixed the problem if it had been confirmed. When Columbia re-entered the atmosphere of Earth, the damage allowed hot atmospheric gases to penetrate the heat shield and destroyed the internal wing structure, which caused the orbiter to become unstable and break apart. So that's why while re-entering, it is very dangerous to enter into Earth's atmosphere. So this is about space shuttle. Next we will discuss about satellite and spacecraft. That is, what is exact difference between a satellite and a spacecraft. So a spacecraft is a vehicle or device designed for travel or operation outside the Earth's atmosphere, whereas a satellite is an object that orbits the Earth, the Moon, or another celestial body. So from the GIF which we see here is that there is a rocket, it is launched. Once it is launched, in the capsule in the top region we have spacecraft placed. Inside the spacecraft we have the satellite. So we will launch a rocket, we will launch the rocket through a space launch vehicle. It will get burned, it will exit the Earth's atmosphere, it will reach a certain altitude, and then the other stages will be discarded. Then only the spacecraft will be remaining. So once the spacecraft is reached to a particular region, it will also get discarded and it will place the satellite into the orbit. And then this satellite will continue to orbit around the specified body. It may be Earth, it may be Moon, or any other celestial body. So this is the basic difference between a satellite and a spacecraft. The Chandra X-ray Observatory and the Hubble Space Telescope are spacecrafts that are in orbit around the Earth. So they are also artificial satellites. So there may be a case where satellite and spacecraft will be the same. So the Chandra X-ray Observatory and the Hubble Space Telescopes are spacecrafts as well as artificial satellites. The Moon is a natural satellite of Earth and Jupiter's moons are natural satellites of Jupiter. The Voyager and Pioneer spacecraft are not satellites because they are not in an orbit around any object. So this is the basic difference for satellite and spacecraft. Next we will discuss about space debris. So space debris, also known as space junk, is defunct artificial objects in space, principally in Earth orbit, which no longer serve a useful function. These include derelict non-functional spacecraft and abandoned launch vehicle stages, mission-related debris, and particularly numerous in Earth orbit, fragmentation debris from the breakup of derelict rocket bodies and spacecraft. In addition to derelict man-made objects left in orbit, other examples of space debris include fragments from their disintegration, erosion and collision, or even paint flakes, solidified liquids expelled from spacecraft, and unburned particles from solid rocket motors. So these are some of the components of the space debris, that is basically the space junk which we humans spread out in the space around the Earth. Space debris represent a risk to spacecraft. Space junk can be hazard to active satellites and spacecraft. It has been theorized that Earth orbit could ever become impassable if the risk of collision grows too high. The ISS, that is International Space Station, also uses Whipple shielding to protect its interior from minor debris. However, exterior portions, notably its solar panels, cannot be protected easily. Although most debris burns up in the atmosphere, larger debris objects can reach the ground intact. According to NASA, an average of one catalogued piece of debris has fallen back to Earth each day for the past 50 years. So, wherever we go, we create garbage and then we do not take care of it. The same has happened for the space where we go for exploration, but in return we place our junk inside the orbits or inside the space, and again this junk itself is becoming harm for our planet Earth. So, this is a picture taken from Hubble telescope where we can see several debris are located inside the space. So the first picture is spent upper stage of a Delta II rocket photographed by the XSS-10 satellite. So this image is taken in space where this rocket is moving freely in the space, while the picture to the right, second one, is Saudi officials inspect a crashed PAM-D module in January 2021. So this has fallen directly from space to the Earth. Then a drifting thermal blanket photographed in 1998 during STS-88. So these are all kind of space debris which one has observed and which has been photographed and taken to spread the awareness about the space debris and take specific precautions. Next, we will discuss about current and future rocket technologies. So first we will discuss some classification of rocket engines, that is rocket propulsion can be classified into thermal and non-thermal. Then again this thermal can be classified into chemical and non-chemical. So chemical propulsion in the sense that we'll be using chemicals to generate that amount of exhaust gases or generate the thrust. So basically by doing combustion, that's why it involves thermal propulsion. So chemical has bipropellants and monopropellants. The name suggests bipropellants, that is using two number of propellants, while as monopropellants suggest using one single propellant. So under bipropellants we have solid, liquid, hybrid, that is using solid fuel and oxidizer, liquid fuel and oxidizer, or hybrid, that is either one is solid, other one is liquid. Then again this liquid and hybrid can be classified as pressure fed or pump fed systems. So this is about the chemical propulsion. Next we will discuss about non-thermal, non-chemical propulsion. So this includes nuclear, beamed, cold gas, solar, electrical and advanced. These are some of the non-thermal, non-chemical propulsion systems. Then again, the electrical propulsion can be classified into electrodynamic, electromagnetic, electrothermal and electrostatic. Then one more classification we can see under electrothermal is resistor jet and arc jet. Lastly, for electrostatic we have ion propulsion and colloid propulsion. More of for advanced we have solar thermal and laser. This is the overall classification of a rocket engine, and out of this some of the technologies like solid, liquid, hybrid are used for some rocket systems, while some small rockets also used electrical propulsion. So we'll discuss some of them in detail. So first one, that is chemical rocket engines. That is the energy from a high pressure combustion reaction of propellant chemicals, usually a fuel and an oxidizing chemical, permits the heating of reaction product gases to very high temperatures, that is around 2500 to 4100 degrees Celsius. These gases subsequently are expanded in a nozzle and accelerated to high velocities, that is around 1800 to 4300 meters per second. So such high velocities are needed to be expanded in nozzle to get more amount of thrust so that the rocket can be escaped with the escape velocity of 11.18 meters per second. So according to the physical state of the propellant, there are several different classes of chemical rocket propulsion devices. These are solid, liquid, gaseous and hybrid. So this is the typical types of chemical rockets, that is liquid propellant and solid propellant. So basically in a solid propellant rocket engine, solid fuel and solid oxidizers are used and they are burned entirely when the rocket is launched. While as for liquid propellant rocket engines, fuel and oxidizer are present in liquid states and they are stored into different storage tanks. So when the launch is going to happen, they both are allowed to enter inside the combustion zone through different pipes and arrangements, and then with the help of igniter, they are ignited. Thus, when the entire propellant is burned, still the rocket has to carry the weight of the storage tanks and the infrastructure associated. So each of them have its own pros and cons, like solid propellant rocket boosters have no moving parts, but liquid does have, and so much complexity is involved in liquid propellant rocket engines. While for liquid propellant rocket engines, we can control the amount of thrust generation. The same is not happening with solid propellant rocket engines. So this is about chemical rocket engines, and many countries use this for high thrust generation during launch missions. Next we will discuss about nuclear rocket engines. So two different types of nuclear energy sources have been investigated for delivering heat to a working fluid, usually liquid hydrogen. However, none can be considered fully developed today and none have flown. They are the fission reactor and the fusion reactor. Both are basically extensions of liquid propellant rocket engines, and the heating of the gas is accomplished by energy derived from transformations within the nuclei of atoms. So this kind of reaction happens at very molecular level in between the nuclei of atoms. So in the nuclear fission reactor rocket, heat can be generated by the fission of uranium in the solid reactor material and subsequently transferred to the working fluid. There were concerns with the endurance of the materials at the high temperatures and intense radiations, power level control, cooling a reactor after operation, etc. So no further ground tests of these rocket engines have been undertaken. Fusion is an alternative way to create nuclear energy which can heat a working fluid. A number of different concepts have been studied. To date, none are feasible or practical. So this is one aspect of propulsion where nuclear energy can be used to generate high amount of thrust, but till date none of the ideas have worked and none has gone till the ground tests of any rocket propellant using nuclear energy. Next we have electric rocket engines. So in an electric propulsion, the source of the electric power, that is nuclear, solar radiation receivers or batteries, is physically separate from the mechanisms that produces the thrust. In electrothermal rocket propulsion, propellant is heated electrically by heated resistors or electric arcs, and the hot gas is then thermodynamically expanded and accelerated to supersonic velocities through an exhaust nozzle. So for electric propulsion, the source of the electric power is physically different than the mechanism that produces the thrust. So under electric propulsion, we have electrothermal rocket, electrostatic rocket, and electromagnetic rocket. So each of them work differently. So in an electrostatic rocket or an ion rocket, a working fluid, typically xenon, is ionized by stripping off electrons, and then the electrically charged heavy ions are accelerated to very high velocities, around 2000 to 60,000 meters per second, by means of electrostatic fields. The ions are subsequently electrically neutralized. They are combined with the electrons to prevent the buildup of a space charge on the vehicle. While as lastly in an electromagnetic or magnetoplasma rocket, an electrical plasma, which is an energized hot gas containing ions, electrons and neutral particles, is accelerated by the interaction between electric currents and magnetic fields and ejected at high velocities, that is around 1000 to 50,000 meters per second. So these are different electric propulsion means through which we can achieve a space launch, but most of these are used in space and not on the Earth's surface. Next we will discuss about Falcon 9 reusable rocket. So lately we all have heard about this Falcon 9 rocket. So we will discuss what is its speciality and why it has been so much famous in today's date. Falcon 9 is the world's first orbital class reusable rocket designed and manufactured by SpaceX. SpaceX is an American aerospace manufacturer and space transportation services started back in 2002 with the aim to reduce the space transportation costs. So the Falcon 9 is manufactured by SpaceX, whose aim is to reduce the space transportation costs. So it is partially reusable two-stage to orbit medium lift launch vehicle. Reusability allows SpaceX to refly the most expensive parts of the rocket, which in turn drives the cost of the space access. Both stages have liquid propellant Merlin rocket engines. So Falcon 9 has two stages attached, which are liquid propellant rocket engines. The payload section consists of Dragon capsule. Dragon is the class of reusable spacecraft. Again, this company is using the same stages again, that is reusing the stages again. Also, they are reusing the spacecraft which has been already used. So it is the only spacecraft flying that is capable of returning significant amount of cargo to Earth and is the first private spacecraft to take humans to the space station. So we'll discuss about the journey of this Falcon 9. So 1 minute and 10 seconds after liftoff, it reaches supersonic speed, and at approximately 158 seconds into flight, the first stage engines are shut down, which is called as main engine cutoff. That is, the two stages will be discarded. With the help of cold gas thrusters, the main engine fell into the earth. After 8 seconds, second stage Merlin vacuum engine ignites to begin a 7-minute burn that brings Falcon 9 and Dragon into LEO. So after discarding the second stage, it will go for a 7-minute burn to reach the Dragon capsule into LEO, that is low Earth orbit. So within short amount of time, so many activities are performed, and one of the best feature of Falcon 9 is that the stages which are discarded, they land back to the Earth in proper position. So the booster is programmed to follow a precise flight path return back to Earth, and it must autonomously perform a series of controlled maneuvers in order to maintain that path and land vertically on the landing pad. So there are three types of flight controls used, that is cold gas thruster, grid fans, and reignitable engines. So with help of these three controls, the landing of the Falcon 9 stages vertically on the launching pad is possible. In total of 8 nitrogen cold gas thrusters are used to control the orientation of rocket, which uses the expansion of a pressurized gas to generate thrust, particularly used for flip maneuver after stage separation. Then it is deployable grid fins, that is 4 titanium grid fins are mounted at the top of the first stage booster. These are aerodynamic control surface that used for precise control of the rocket's position and orientation prior to landing. These fins alone are primarily responsible for the incredible 10-meter landing accuracy. So these fins are provided for Falcon 9 stages, which gives around 10-meter landing accuracy. Then it is reignitable engines, that is, since the first stage must perform 3 separate burns after stage separation, it is necessary for the main rocket engines to be reignitable. So it will perform 3 burns, that is, first burn will be during the launch, the entire launch, and second burn will be when it is discarded, so it has to enter the Earth's atmosphere, and the third burn will be when it is landing back to the launching pad. So that's why the stages which are made, that is liquid propellant for Falcon 9, are reignitable. The engines of the first stage booster are therefore designed so that they can reignite. So these are the 3 controls which are used for Falcon 9's landing back vertically on the launch pad. So in the GIF we can clearly see that the grid fins are used and cold gas thruster is burned and it is landing vertically. So in total till now 154 total launches are done for Falcon 9, out of which 114 are done landings till now and 93 are reflown rockets. So this is very incredible stats for SpaceX company. It also has an inertial navigation system and global positioning system. Deploying landing legs are also used in order to perform vertical landing. So we can see that the legs are getting deployed so that it can land vertically. It has 4 lightweight landing legs constructed of carbon fiber and aluminium and contains an impact attenuator for particularly hard landings. After 35 days of work completing of Dragon at space station, the crew will release the vehicle. It takes approximately 30 minutes to Dragon to re-enter the Earth's atmosphere. Then it is splashed down into the Pacific Ocean. Then again it is recovered with the help of ships and the data is collected back. So this is the current and latest technology used for rocket propulsion, where the stages are reused, the spacecraft is reused for next missions, and the space transportation cost is also reduced. Now we will discuss some of the future rocket engine technologies, that is chemical rocket propulsion we will discuss, then we have a combination of solar electric propulsion, then nuclear thermal electric propulsion, all 3 different varieties of thrust generation, then electric ion propulsion, and lastly electromagnetic propulsion. So the US Defense Advanced Research Projects Agency has recently commissioned three private companies, that is Blue Origin, Lockheed Martin, and General Atomics, to develop nuclear fission thermal rockets for use in lunar orbit. Such a development, if flown, could usher in a new era of spaceflight. That said, it is only one of the several exciting avenues in rocket propulsion. So, as discussed, many ideas have planned till now for nuclear rocket, that is using the nuclear energy, but none has flown till now. So let's hope for the best that we will soon get nuclear energy rockets. So we will start with chemical propulsion. So there is one engine called Raptor engine. We will discuss about it. So Raptor is a family of full flow staged combustion cycle rocket engines developed and manufactured by SpaceX for use on the in development SpaceX Starship, which is a fully reusable super heavy lift launch vehicle that is currently being developed. So full flow staged combustion, that is FFSI, which is shown in the image, is a twin shaft staged combustion cycle that uses both oxidizer rich and fuel rich pre-burners. The cycle allows full flow of both propellants to the turbines, hence the name is given. The fuel turbopump is driven by the fuel rich pre-burner and the oxidizer turbopump is driven by the oxidizer rich pre-burner. Benefits of the full flow staged combustion cycle includes turbines that run cooler and at lower pressure due to increased mass flow, leading to a longer engine life and higher reliability. So with the help of twin shaft staged combustion cycle of this FFSC engine, which is incorporated in Raptor engine, will be more reliable and will give longer engine life because of increased mass flow inside the engine. So the rocket will consist of the super heavy booster stage and the Starship spacecraft on top and will be mainly constructed out of stainless steel. In total, Starship is the tallest, heaviest and the most powerful rocket ever built. Both stages combust liquid oxygen and methane with variants of Raptor engine. So this engine will be used on these stages of the Starship rocket, which is being developed by SpaceX. The Raptor engine is powered by cryogenic liquid methane and liquid oxygen, which is called as Methalox, rather than the RP-1 and liquid oxygen, which is called as Kerorox, used in SpaceX prior Merlin and Kestrel rocket engines. So SpaceX itself is creating different kinds of varieties for rocket engines. That is, first it was Merlin engine and Kestrel engine. Now it is constructing the Raptor engine, in which it is using the combination of cryogenic liquid methane and liquid oxygen. Raptor is used in Starship system in both the Super Heavy Lift, Super Heavy Booster and in the Starship spacecraft, which acts as the second stage when launched from Earth and as an independent spacecraft in LEO and beyond. So this Raptor engine will be used in different parts of the entire rocket of Starship. Starship is planned to be used in various applications, including Earth orbit satellite delivery, deployment of a large portion of SpaceX Starlink satellite constellation, exploration, moon landing, and colonization of Mars. So this is one future technology which is being developed by SpaceX, that is the Raptor engine. Next we will discuss about one more engine which is called as SABRE engine. That is, at Reaction Engines in the UK are developing the Synergetic Air Breathing Rocket Engine SABRE, what we think will be the next generation of space propulsion technology. Their aim is to enable horizontally launched reusable space vehicles that are affordable, reliable and responsive and can be launched at a high and regular frequency. It basically tells us that everything carried on board a vehicle has a penalty in the form of additional propellant and structural mass of the vehicle needed to get it off the ground. In other words, this approach hampers mission performance, mission payload and mission time for conventional rockets. SABRE, on the other hand, is a hybrid air-breathing rocket engine. During the atmospheric segment of its ascent, it will use oxygen from the atmosphere instead of carrying it inside the vehicle before switching to onboard oxygen upon leaving the atmosphere. A SABRE-powered launch vehicle will therefore have lower mass for a given payload than a conventional rocket vehicle. This mass benefit can be traded for systems that will enable reusability and aircraft-like traits such as wings, undercarriage, and thermal protection systems, all the features needed to fly the same vehicle over and over again, achieving hundreds of launches. So this is the idea of reaction engines which is being developed at UK where they are planning to enable horizontally launched reusable space launch vehicles, where overall mass of the system will also be reduced and reusability can be done at very high level. So this is the general picture of the established SABRE engine. So it is more like a hybrid air-breathing rocket engine. It has rocket parts, it also has the aircraft engine parts, that is jet engine parts. First one, that is, it has an air intake, nose spike air intake is there. And we have a pre-cooler, we have a compressor inside which the kinetic energy will be converted to pressure energy. We have bypass duct. Then we have turbine and thrust chamber through which the thrust will be generated. And lastly, the nozzle. SABRE is a new class of engine for propelling both high-speed aircraft and spacecraft. It is unique in delivering the fuel efficiency of a jet engine with the power and high-speed ability of a rocket. There are three core building blocks to SABRE: the pre-cooler, the engine core, and the thrust chamber. Each of these systems can be developed and validated using ground-based demonstrations, which saves cost and time relative to flight tests, a design feature that benefited the development of the propeller and jet engine. Reaction engines are demonstrating each of these tests independently. The high-temperature test of the pre-cooler took place in 2019. Testing of the core engine components and pre-burner have taken place during 2020 and 2022. So this is the next chemical propulsion technology developed by reaction engines, and still the tests are going on. Once it is validated with all the tests, this engine can be seen flying over us, which is a hybrid combination of air breathing and non-air breathing propulsion. Next we will discuss about solar electric propulsion. So solar electric propulsion could be used to send cargo to Mars ahead of a human mission. With solar electric propulsion, large solar arrays unfold to capture solar energy, which is then converted to electricity. This powers something called a Hall thruster. There are pros and cons. On the upside, you need far less fuel, so the spacecraft becomes lighter, but it also takes your vehicle longer to get there. Aerojet Rocketdyne is working on a Hall thruster for the Gateway, a proposed space station in lunar orbit. Solar is the best because we know we can scale it up. Joe Cassidy, that is Executive Director of Aerojet Rocketdyne Space Division, has explained. So they are utilizing the Hall thruster energy to create a proposed space station in lunar orbit. So this is the solar electric propulsion device designed by Aerojet Rocketdyne. According to them, we have already got these flying today on communication satellites. The power level we fly at today is 10 to 15 kilowatts, and what we are looking to do with the Gateway is to scale it up to something greater than 50 kilowatts. Mr. Cassidy said, Aerojet Rocketdyne's Hall thruster will be much more fuel efficient than the liquid hydrogen and oxygen rocket engines. But a good way to make access to space cheaper would be to have fewer launches, he also explains. So this is about the solar electric propulsion. Next we have the combination of three different energies, that is nuclear, thermal and electric propulsion. So here another idea is to use chemical rockets to lift off from Earth and to land on Mars. But for the middle part of the journey, some engineers propose using something called nuclear thermal electric propulsion. Astronauts could be sent to the Gateway in NASA's Orion capsule. The Orion crew capsule would then dock with the transfer vehicle. So once this Orion has been connected to the transfer vehicle, a nuclear electric rocket would be used to get the crew capsule and the transport module to Mars, where they link up with the Mars orbiter and lander, which are waiting in Mars orbit. In a nuclear thermal electric rocket, a small nuclear reactor heats up liquid hydrogen. The gaseous form of the element expands and shoots out of the thruster. Boeing is not so keen on nuclear thermal propulsion because it worries about the effects a nuclear reactor might have on astronauts. Today's advances in material testing capabilities and reactor development are providing momentum for NASA in partnership with the Department of Energy to mature functional nuclear thermal propulsion components needed to support a subscale engine demonstration. So this way, the nuclear thermal electric propulsion can be used with steps. So that is, first with the help of chemical rockets, the crew and the payload will be lifted off from Earth. Then these astronauts will be sent to the Gateway, that is the proposed space station in lunar orbit, and then these astronauts will dock with the transfer vehicle. So then this Orion capsule will be connected to a transfer vehicle, which will be a nuclear electric rocket. Will use a small nuclear reactor which will heat up the liquid hydrogen, and this will create enormous amount of energy which will expand through the nozzle, and the Orion capsule will reach near to the Mars orbiter and lander, and then they will create a connecting link for the orbiter and landing, and they can land on the Mars. Next, to keep the round-trip crewed mission duration to about 2 years, NASA is looking at nuclear-enabled transportation systems to facilitate the shorter stay class of missions, taking advantage of optimal planetary alignment for a low-energy transit for one leg of the trip, and using the new technology to make the higher energy transit for the other leg. NASA is looking at two types of nuclear propulsion systems, thermal and electric, for human missions to Mars, specifically for stay of up to 50 days in the vicinity of Mars, 30 days on surface, and an overall mission duration of no more than 2 years. To meet this mission duration, a nuclear electric system would need a large chemical stage to meet the overall thrust capability needed for a human Mars mission. So this is kind of nuclear thermal electric propulsion system which is still in the conceptual phase, and NASA is looking for different kind of systems. But still, if this is possible, we can explore many things of the Mars within short amount of time and with less number of energy. Next, we will discuss about electric ion propulsion. Here we have Bessemer engine. So we will see what is this engine in detail. Electric ion propulsion generates thrust by accelerating ions, that is charged atoms or molecules, using electricity. Ion propulsion is already being used to power satellites in space, but they produce only a low thrust, more like the power of a hairdryer, and therefore have a low acceleration, but given time they can reach high speed. And Astra says it is working on a type of thruster called the Bessemer that uses radio waves to ionize and heat a propellant and then a magnetic field to accelerate the resulting soup of particles in the plasma. Plasma is designed to produce much more thrust than a standard ion engine. The Variable Specific Impulse Magnetoplasma rocket, which is the name of the Bessemer, that is Variable Specific Impulse Magnetoplasma rocket engine, is Astra's flagship project, a disruptive development in the space propulsion status. It is the product of more than 25 years of NASA and Department of Energy R&D in plasma physics and space propulsion technology, plus 15 years of added technology maturation in the private sector of Astra rocket company. So Bessemer is the engine which is mostly combination of many different energies, electric ion energy and magnetoplasma energy. So we'll see how it works. In Bessemer engine, a high-power electric rocket engine suited for a wide range of missions from economically sustainable logistics operations in space to high-speed transport in deep space. In the Bessemer engine, powerful radio frequency waves are launched by special antennas. We call them as couplers, that is the Astra company call these as couplers, wrapped onto a ceramic tube where a propellant gas is fed. The RF ionizes the gas, turning it into a plasma, a very hot electrically charged gas. A strong externally applied magnetic field confines, guides, and ultimately accelerates the plasma, letting it escape to provide useful rocket thrust. Unlike most chemical rockets that need complicated pumps and turbo machinery, the Bessemer does not have any moving parts. It is comprised of a two-stage rocket core, each stage with its own radio frequency coupler. A unique feature of the Bessemer engine compared to other rockets is its ability to vary its exhaust parameters, thrust and specific impulse while operating at a fixed total power level. So first they have to ionize, then energize, and then accelerate. So this way the electric ion propulsion or the Bessemer engine of Astra will work, and still the tests are going on for the same engine, and once it is validated it will be soon seen in space. Next we have electromagnetically powered flights, that is the last one. So Escape Dynamics, a Colorado startup company that focuses on electromagnetically powered flight systems, has successfully tested a rocket thruster powered by microwave energy, and its performance actually surpassed the limit of chemical combustion rockets. Escape Dynamics envisions its space plane will be propelled by ejecting hydrogen and heated with microwave energy. In order to send rockets to space by beaming power at them, energy must be drawn from the electric grid, converted into microwaves using a gyrotron guided through a system of beam shaping mirrors and beamed from an antenna to a thruster. This is how it works for now during initial testing phases at least. So Escape Dynamics, a startup company from Colorado, is planning to use the microwave energy, and they have aimed for performance where it actually surpassed the limit of the chemical combustion rockets. During testing, the company converted the microwave energy into thrust with a thermal thruster that contained a high efficient microwave absorbing heat exchanger. The heat exchanger was designed to capture more than 90% of the incoming microwave energy and the heat the propellant flowing through it towards the nozzle. Escape Dynamics will now move testing out of the lab and into the desert, and if all goes well, it will start flying drones with microwave beam. So these are the initial plans for the Escape Dynamics for the electromagnetic powered flights, where they will be using the beam energy to fly the rockets. So this is an artistic concept on how Escape Dynamics spaceship will fly. So the microwave energy will be focused at the particular vehicle, and then with the help of this microwave energy they will be allowed to fly. So this covers the future rocket technologies which are being planned. There might be some more technologies, but some of these are listed here and explained. So the summary for today's class is, first we discussed about various rocket systems, that is structure, guidance, payload and propulsion systems, and studied with their applications associated with the rocket. So we have seen that what are these four different systems and why they are needed, what are different components included inside these systems. Then we saw two types of rocket staging, that is serial and parallel. Also we discussed that why rocket staging is done and what happens to the detached stages. Then we discussed about various space transportation technologies and vehicles used today. So we have seen about escape velocity, what is the escape velocity for Earth and how it varies from planet to planet. Then we have seen space launch vehicles, different space launch vehicles of countries, and for our country India. Also we discussed about different types of orbits in which the satellites are placed. We also saw difference between satellites and spacecraft. And we discussed about the space debris, the space junk which we generate around the Earth. Next we discussed about current and future technologies of rocket propulsion. That is, we discussed about the classical chemical propulsion, nuclear propulsion and electric propulsion. Also we gone through the entire general classification of rocket propulsion. Then we discussed about Falcon 9 reusable rocket with all its features. That is how it reaches supersonic speeds in less amount of time and what different kind of engines are used. Also we studied how it performs vertical landing with 10-meter landing accuracy of the liquid stages. Then we discussed about future rocket technologies like Raptor engine, Sabre engine, which are basically under chemical propulsion. Then we saw nuclear thermal electric propulsion, solar electric propulsion, electric ion propulsion, and lastly electromagnetic propulsion, etc. So if these future technologies are generated and tested, cleared all the tests, then soon we will be seeing all these discussed technologies in our space. So the references for today's class are present here, and with this we finish this course. Thank you.